Hello and good day, sir. My name is Bender Badr Bahasami, and today me and my colleague will present Lab 2 of our course, which is the flow over immersed body and boundary layer theory. Okay, we'll move on to the table of content. We have four parts in our presentation, which is introduction, methodology, result, and finally discussion and conclusion. Okay, we'll start now with introduction. I'll give a simple background. The boundary layer theory is based on dividing the flow around the body into two regions. An area adjacent to the body called the boundary layer is characterized by significant change in the distribution of the velocity of the liquid and the appearance of large effect on its viscosity. Moving on to the problem statement. The boundary layer, as you are aware, is a hypothetical layer of fluid that forms when a fluid flows along solid flat surfaces. The surface condition, Reynolds number, pressure, and other relevant parameters all affect how the boundary layer forms. Therefore, when a totally submerged body is presented, the external flow of fluid across it behave differently depending on the shape of the object it goes through. In this lab experiment, we will take the variation in velocity, speed, and boundary layer thickness along flat, smooth, or uneven surfaces, as well as the streamline created over various immersed bodies. Okay, sorry. Now moving on to what do we want to achieve or objective. In this lab, we want to determine the flat plate speed distribution, to also determine the boundary layer thickness for both smooth and rough surfaces of a flat plate subjugated to a longitude flow, to calculate the velocity profile for a flat plate flow that is both smooth and rough, and fourth, to visualize the flow pattern over or around different immersed bodies, and finally, plotting streamline over cylinder orifices or wing profile to identify flow conditions. Okay, now moving on to scope. So in scope, what is relevant in our experiment? In this laboratory experiment, we will test various streamline produced because of the effect of flow separation, turbulences, and angles of the flowing fluid. Determine how the fluid flow patterns and boundary layers behave over immersive bodies and the solid surface. Thus, in this experiment, the value of the drag and lift forces at various velocities, as well as the velocity and the height of the water that occurs as the water flows through the submerged object will be measured. We will also compare the outcomes of the surfaces that are rough and those that are smooth. Finally, the observed streamline and speed distribution along the various surface conditions and shapes will be plotted. Okay, moving to the second part, which is methodology. First is boundary layers and the types of boundary layer. So what is a boundary layer? A boundary layer is a thin layer of fluid in the immediate vicinity of a bounding surface, formed by the fluid flowing along the surface. The fluid interaction with the wall induces a no-slip boundary condition. As you can see, there is three types, which is laminar, transition, and turbulent. First of all, the laminar is a smooth flow which creates less skin friction drag than the turbulent flow, but is less stable. Turbulent is an irregular flow that can be characterized by the chaotic and rough movement of particles through a region, and it can transition to laminar once the kinetic energy dissipates. So, what is transitional? The transition is the state in which the flow transition from laminar to turbulent and the other way around. Okay, moving on to flow over immersed body. Simple explanation for it. Fluid flow that circle outside the immersed bodies is referred to as external flow. Without any external boundaries from the surrounding surface, the boundary layer develops naturally. This flow causes pressure that are normal to the surface and shear forces that are parallel to the surface, which together produce lift and drag forces excuse me, on the body. In this image, as you can see, it illustrates how streamline created through an item can be used to depict the flow movement of fluid around a totally submerged body. Please note that the flow characteristics of a particular shaped object depends greatly on a variety of factors, including size, direction, speed, and finally fluid properties. Okay, moving on to calculation. To calculate the Reynolds number, this is the equation. To get everything in the formula, as you can see, there is velocity, pressure, dynamic viscosity, and finally density. These are all the equations or formula that we needed in this experiment. I mean, to get the Reynolds number. Now moving on to Bernoulli theorem. Bernoulli theorem states that pressure increases as the velocity decreases. This pressure is differential is greater than the lift force produced in this way because the air fuel is under high pressure. Thus, the following formula can be used to determine the lift and drag force. As you can see, this is the lift, this is the drag force in Bernoulli theorem. Okay, now moving on to equipment for both experiment. Okay, in experiment 1, or flow over immersed bodies, we will need an airflow bench, a smoke controller, a radial fan speed controller, an airfoil model, and finally a manometer. Okay, moving on to second experiment equipment for flow over flat plate. We'll need a rectifier, a beta tube, and finally a manometer. Okay, now moving on to procedure for both experiments 1 and 2. Okay, now we're working with the procedure of the first experiment. First of all, please turn on the smoke generator for about 5 minutes in advance as it needs to warm up. Then turn on the fan, work with low winds for the best outcomes. Third is to activate the remote trigger, then draw observation and indicate any conclusion, and also change the wind speed and record these outcomes. And please repeat the experiment process with the other two drag bodies, such as wing profile and orifice, and finally draw a profile of the flow streamline. Okay, moving on to the procedure of the second experiment, and it is as follows. First is to take note of both temperature and the surrounding area, so we can verify the air density. Second is to secure the plate with a nerd screw at x equated to 0. Third is using a manometer to obtain the reference level for ambient pressure. Fourth is to increase the wind channel speed to a satisfactory level. Fifth is to draw a profile of the flow streamline. Sixth is to examine the first pressure or dynamic pressure value measured by bringing the beta tube up close to the plate, considering that 0.7 millimeter tube diameter. This value corresponds to a height of y equal to 0.35 meters. And finally, add to the list of measured values to height of 1.5 millimeters. Every 0.25 millimeters is adequate. Up to a height of 5 millimeters, every 1 millimeter is acceptable. And the final step is to repeat this in the difference area. Okay, moving on to result, my colleagues will start his part. Thank you for listening and have a good day.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hilmi bin Zulkifli. My metric ID is MA19141. So I will explain about the result for the experiment 1, which is the flow over immersed body. So in this experiment, the initial head H is given, which is the 137 millimeter. So we need to find the area of airfoil, which is 0.042 meter times 0.15 meter, and we will get the 0.0063 meter square. So the coefficient drag is 0.59 and the coefficient of lift is 0.84. So for the sample calculation, we need to find the drag force and the lift force for this experiment, and also the head difference in the experiment. In the sample calculation, we need to find the head difference by minus the initial head and minus the head of the data given, which at the different fan speed. So the head difference we will get will 4.5 millimeter. So for the calculate force of lift is CL times area and times the difference of head. So the 0.84 times 0.0063 times 4.5, we will get the force lift is 0.028 Newton. For the drag force, it's also the same formula with the lift force, but we will use the drag force coefficient. So 0.59 times 0.0063 times 4.5, and we will get the drag force lift, which is 0.0167 Newton. So in this experiment, there will be three different angle of attack. The first one is the angle of attack at 0 degree, and second one is the angle of attack at 30 degree, and the last one is the angle of attack at 45 degree. So as you can see, this is data that have been calculated for the head difference, drag force and lift force for 0 degree angle of attack. So at the different fan speed, we will see the drag force and the lift force has been calculated. Next is the drag or lift force versus fan speed at the angle of attack 0 degree. As you can see, the increases of the fan speed also will increase the drag or lift force. It also is the same with the data that we get from the angle of attack at 30 degree. With the increasing of the fan speed, the drag or lift force also will be increases. It also the same with the angle of attack at 45 degree. As you can see, the 45 degree of angle attack also with the increases of the fan speed, the drag or lift force also will increase. So that's all from me. Thank you.
Assalamualaikum and my name is Muhammad Adib Haikal bin Zainuddin, and I'm going to present the result for experiment 2, which is experiment 2A. Okay, experiment 2, flow over flat plate boundary layer. There are two types of surface that will be investigated in this experiment. Hence, there will be two experiments to conduct, which is experiment 2A and 2B. Okay, for smooth surface flat plate, this is the data given, the table for head H1. Okay, this is the table that we calculate for delta head. The data we get is from the formula we do the calculation. We use initial head, which is 278 millimeter, and for the formula, delta H equals to initial head minus head H1, and we substitute the value. 278 millimeter minus 257 millimeter, we get 21 millimeter. Okay. Next, for data for velocity. This velocity we get for this formula. Velocity v equals to square root 2g delta h. We substitute the value, which is v equals to square root 2 bracket 9.81 bracket 0.021 equals to 0.96419. Then we do for all the data and we get this table. Okay, for Reynolds number, we use this formula, which is RE equals to rho VL equals over mu. Rho equals to 1.184 kg per meter cube. Mu is equals to 1.849 times 10 to the power of negative 5 kg per meter square. Hence, we substitute the value for rho. We get we use 1.184 G V. We use the data in the table 0.6419, and for liter we use the L, which is the plate distance, which is 0.02 over 1.849 times 10 to the power of negative 5. We get 781.9907. Okay, here is our graph. The boundary layer thickness versus velocity meter per second. That's all from me.
ورحمة الله وبركاته. I'm Faisal Mustafa Al-Attas. Matric number 19157. I will complete the result. So now we have a rough surface flat plate. Firstly, this table shows the boundary layer thickness versus head H1. For sample calculation, we have initial head equal 278 and delta H equal to 4. So now this table shows boundary layer thickness to head H1, as you can see. For sample calculation, for velocity, we have square root 2 delta H. So velocity equal 0.2801. Now this table shows boundary layer thickness versus velocity, as we can see in this table. So now we have Reynolds number versus boundary layer. In simple calculation, we can see Reynolds number equal 1.184 multiplied by 0.6419 multiplied by 0.02 over 1.849 multiplied by 10 to the power of minus 5. This table shows boundary layer thickness versus Reynolds number. So now we have boundary layer versus velocity. This graph shows boundary layer thickness versus velocity. You can see velocity starts from 0.200 until 0.800. So now we have a boundary layer versus velocity for smooth surface at one selected plate distance x equal to 80. We can see in this table smooth surface and rough surface for boundary layer thickness from 4 until 32. So here we have speed distribution for smooth surface and rough surface, as we can see in this plot. Now for discussion, firstly for experiment 1. Which body creates the most smooth streamline? Since the fluid channel can be quite short, the fluid is flowing slowly and its viscosity is generally high. The body that produces the cleanest streamlines is at 0 angle. Secondly, what does a smooth streamline portray? Laminar flow denotes smooth, regular airflow pattern around an item. It denotes a limitation of the disruption of the air caused by the object's travel through it. Thirdly, what happens to the wing profile at 30-degree angle compared to the normal? The separation point advances and reaches maximum limit. Lastly, what phenomenon causes the orifice flow to disperse from your knowledge? The Ventro effect is caused by the decreases in flow pressure that occurs when a fluid passes past a confined segment or choke of a pipe. Now for experiment 2, firstly explain about the boundary layer thickness and the boundary layer of both surfaces. Surface roughness has a significant influence on the flow. From the experiment we can see that the turbulent region of a rough surface is having in the lower number of Reynolds number, while the turbulent region of a smooth surface is having in high number of Reynolds number. Secondly, what is the distance in the plate before the flow becomes turbulent? What phenomenon could be the reason of this change? The distance in the plate before the flow becomes turbulent is 40 mm. An increase of the plate distance will cause this change. This is because the viscous layer region becomes smaller and viscous effects are only imported inside this region. Hence, the flow will be distributed. We can determine whether a region is laminar or turbulent using critical Reynolds number. Critical Reynolds number is the limit where a laminar flow changes to turbulent flow. If the calculated Reynolds number is greater than the critical Reynolds number, then the flow will be turbulent. Lastly, what are the differences in terms of result for smooth and rough surfaces? The surface roughness of rough surface is higher than the surface roughness of smooth surface. Therefore, at 20 mm boundary layer thickness, the velocity of the flow on smooth surface is higher than the velocity of the flow on the rough surface. Lastly, we have the conclusion. The experiment has been performed successfully. The experiment's goal of determining of the border thickness of a treated plate have all been met. The fan speed values of experiment 1 are different. We employ 8 different fan speeds for each angle, ranging from 0 to 30 to 45 degrees. According to the statistics, as the fan speed increases, so do the force and velocity. When the fan speed remains constant, the angle of the usage increases, as does the force. There are rough surface and smooth surface. Utilized in experiment 2. When the thickness of both boundary layers increases, the head and velocity rise as well. Furthermore, the Reynolds number rises. That's all. Thank you.